Guys, welcome to our first video here. We're going to dig right into chapter 29, which is picks up right where we left off before break, which was a long time ago. Before break, we were talking about the force that a charged particle experiences due to a magnetic field, and we made some observations about that. We noted that in order for a charged particle to experience a force from a magnetic field, it has to be moving. And we also noted that the direction of the force is going to be perpendicular both to the velocity and to the magnetic field. So there was a cross product in there as well. But today, what we're going to start to think about, and what chapter 29 is all about, is calculating the magnetic fields themselves. So if in chapter 28 we just sort of assumed that there was this magnetic field, now we're actually going to look at where that magnetic field actually comes from. And it's sort of pleasing and symmetric that the magnetic field itself comes from currents, from moving charges. So moving charges respond to magnetic fields, but moving charges also create magnetic fields. And so we're going to start today thinking about how to calculate those magnetic fields due to currents. There's going to be two laws that we're going to discuss. The first one is called the biot law, and the second law is called Ampere's law. The biot law is in some senses more general. It can be used in any case, but it's sort of tricky and cumbersome to use. Ampere's law is kind of like Gauss's law. You can't use it for all cases, but just like Gauss's law made it very convenient under certain circumstances to calculate electric fields, similarly Ampere's law under certain circumstances, will make it much more convenient for us to calculate magnetic fields. So let's just get right into it. So I'm going to imagine, I don't know if I can do this. Bear with me. I'm going to see if I can, just kind of make the paper your whole screen here. And I actually, you know what? I think I'm going to do this. I think I'm going to turn it lengthwise. So I think what I'm going to do is focus that. So let's imagine we've got some long wire here, and for our purposes, we could imagine that this wire is infinitely long. Just for our purposes, so there's my long wire, and I'm going to imagine that it has a current, a constant current I, which is, we'll say, directed up towards the top of the page. And maybe I'm interested in finding, so if we just, again, imagine this wire is infinite, maybe we're interested in finding the magnitude of the magnetic field at this point right here, point P, which is a distance away from the wire. I'll call this distance here x. Now, if we started just thinking to ourselves, okay, what might the magnetic field depend on? What is it sort of sensible to think that B would depend on? What are the factors? One of the things that it might be clear to you that B should depend on is the distance x. So somehow B should depend on distance. And it also might make sense to you that there should be an inverse square law. It should somehow be proportional to 1 over r squared. Just since we've seen that a lot, it maybe is predictable that we would see that. And in fact, we will see that. So it should, I think it makes sense. It should depend on distance. By the right-hand rule, since we had a cross product when we were calculating forces due to magnetic fields, it might make sense that there'd be a cross product here. In other words, that the direction of B is always going to be perpendicular to the direction of the velocity of the charges, that is the direction of the current, so that we might get a cross product here. And of course, it might also make sense that the magnitude of B is going to be in some way proportional to the amount of current. That is also true. So these are three things that we might predict reasonably, and they are in fact true. Now, what's tricky about doing the calculation, though, what you might have already picked up on, is if I imagine the various points along this wire, each point has a unique distance to this, or each point along the wire has a unique distance to this point right here. Or maybe not unique, I guess there's 2 points that would have the same distance on either side of the wire. We'll actually utilize that fact. But the point is that as I move along the wire here, I'm getting different distances as my vertical distance changes. So I'm going to have to somehow factor that in. So let's imagine, for instance, we just are thinking about a little piece of the wire right here, this little tiny piece of the wire. Let's imagine this little piece of the wire. I'm going to say it has a length ds. It has an infinitesimal length ds. And I'm going to define ds as a vector. And the direction of the ds vector, I'm going to say, is in the direction of I. I'm going to see if I can't focus this a little bit better. I wonder if there's a, bear with me here as I figure this out, because that doesn't seem particularly focused. Ah, that looks better, doesn't it? Okay, let's stick with that. So ds, again, has the same direction as I. So the direction of ds would be in this direction here. So that means that there is a vector r, which would be the distance from ds to the point in question. So I could introduce a vector like this. This would be the vector r. I'm going to try to stick, when I write lowercase r, I'm going to try to just stick to the convention of lowercase r is a variable. So this this vector r is, of course, also related to the distance between this point right here and ds, and I'll call that, for our purposes, I'll call that distance right here y. So x is constant, but y is going to vary, and therefore r will vary. The distance r will vary, and so that's gonna impact our first assumption up here. Now, I'm not going to go through the hassle of deriving all of the biot-savart law, but I'm going to sort of try to summarize these different facts. So there's going to be a vector here, and it might be worth thinking for a moment, what would be the direction of the little amount of magnetic field due to this current? And you might be able to think about it in terms of the right-hand rule and figure that the direction there is going to be into the page. So maybe I'll introduce a new color here. Here's green. So there's going to be a little infinitesimal here, a little infinitesimal dB. That green is dying. dB vector that's going to be into the page right there. And that dB vector, if I wanted to write an expression for it, might be something like this. dB is going to be equal to some constant, and we'll come back to what the constant is. There's always some constant, right? So we have some constant out there. And then it's going to depend on I, so the magnitude of I matters. I need to get a cross product in there, and the cross product is between the vector ds and r. So I'm going to write ds cross r. And I need to get a 1 over r squared value in here as well. So on the bottom, I want to have an r squared. The problem here is if I put r squared and I have an r up here, then I don't have the inverse square law. There's two ways of getting around this, and I'll do the way that I'm used to seeing, which is we call this r squared, and then we just make this a unit vector, r roof. Sometimes you'll see in books they'll call this r, and they'll just call that r cubed, and that's fine. It's, it's the same thing, but it looks more impressive this way. If you put in the little unit vector, it's more intimidating. So this then incorporates all of these different assumptions that we made. Now the only remaining question is what goes in the box, and what goes in the box is going to be similar to our electric constant. When we had electric fields, we had K, which was 1 over 4 pi times epsilon naught. And we are going to have something, we're going to have a 4 pi in here. So here's the 4 pi. But rather than having epsilon naught involved, we have a new thing called mu naught. And the mu naught goes on the top here. So here's mu naught. I don't know how well you can see that. This is, maybe I'll write this over here. This right here is mu, the Greek letter mu naught. And this is called the permeability constant, or the permeability of free space. Just like epsilon naught was the permittivity of free space, of vacuum, this is the permeability. I'm not going to go into the details of what this is right now, but we can just note that mu naught, the value of mu naught, maybe I can write it over here, is going to be exactly equal to 4 pi times 10 to the negative 7th. So that's our constant that is going to appear in these calculations. So what I'd like to do is to see if we can use this, and maybe I'll write the more general expression then. If that's dB, then we could say that the magnitude of the B vector in general is going to be equal to mu naught over 4 pi times the integral of I times ds cross R roof all over R squared. And this now, if we read it that way, this is the biot-savart law. Very sort of intimidating, impressive looking expression. So this is the biot-savart law. Two French physicists, Biot and Savart. So now I'd like to see if we can use this to actually do the calculation out of what is the magnetic field there. And we're going to see it's not really all that fun of a process to go through. And I'll just promise you that later on when we get to Ampere's law, we're going to see that there is, in fact, a much simpler way of finding the magnetic field for this particular case once we know Ampere's law. So bear with us. It's important that you know this because there are some cases in which you can't use Ampere's law. So we do need to know the biot-savart law. So I'm going to go ahead and try to write this out. I'm going to say B then is going to be equal to the magnitude of the magnetic field is going to be equal to mu naught over 4 pi. And now I'm going to integrate here I times ds cross r. Now, how am I going to write ds cross r? Well, the easiest way of thinking about this is by remembering that the cross product is multiplying perpendicular components. So I could write this as ds times the sine of theta. Or theta, just so we're clear on what I mean by theta. Theta is this angle. It's the tail-to-tail angle between ds, which is this way, and r, which is that way. So theta is always the tail-to-tail angle between the two vectors in the cross product. Since R roof has a magnitude of 1, I don't need to put r in here. I can just rewrite the whole cross product as simply sine theta, ds sine theta. And that's all going to be over r squared. You might think about our limits. The way I'm going to do this, I think, is I'm going to imagine, since this is infinitely long, I'm going to take, well, actually, let's hang on to what we're going to call the limits. I'm going to put the limits in later because I'm going to actually change this theta here, this sine theta, in a minute. So I won't put the limits in yet. So how could we rewrite sine theta? We have an issue here, right? Because the thing that's actually varying is theta, but ds and theta have different dimensions. So there's a couple different ways you can transform this. I could transform this all into, I could get a d theta in here. There's a way of doing that, which might make more sense to some of you. The standard way of doing this, and so I'll teach you sort of the standard way, is actually to transform the sine theta into a dimension of meters. And the way I'm going to do that is to recognize, if I go back to the geometry here, if I go back to my right triangle, if this is theta, then sine theta is simply x over r. And r is just going to be, by the Pythagorean theorem, the square root of x squared plus y squared. So that means I can rewrite this whole expression now as mu naught, and maybe actually I'll pull the I out since we know that I is constant, times 4 pi times the integral of sine theta. I'm going to rewrite that as x over r, where r is equal to, maybe I'll just so I don't confuse you too much, I'm going to write r as the square root of x squared plus y squared. So x squared plus y squared to to the power half. So that means what I'm going to end up with here, if I do that substitution down here as well, then I'm going to get, what is this going to be? This is going to be x over x squared plus y squared to the power 3 by 2. I think I've done that right. So just to remember where this is coming from, r squared is this whole thing right here squared. So r squared is simply x squared plus y squared, and sine theta, I forgot my ds over here. Sine theta is equal to x over the square root of x squared plus y squared. So I have x over the square root of x squared plus y squared times x squared plus y squared, which is x squared plus y squared to the power 3 over 2. This is ds. So now we have our dimensions work, because the thing that's varying is y, and that's and ds and y have the same dimension. So I could even, if I want to, I could call that dy if I want. That's fine. Now let's think about our limits. What should our limits be? Well, I might think about thinking about y from 0 to infinity and the lower half of the wire and just multiply that by 2. So I might take it from 0 to infinity and just put a 2 out front. And that's going to turn this whole thing into mu naught I over 2 pi times the antiderivative of this whole thing, which I'm not going to bother to do out the whole antiderivative, but this whole thing is just going to turn into, if I'm going to put a y here, y over x squared plus y squared to the power half, taken from 0 to infinity. Okay, and that's with an x here as well. So this integration, this is one of those integrals where if you're thinking, if you try to do this on your own and you're having a little bit of difficulty getting from here to here, this is one of those integrals that's just given in an integral table on the AP exam. So this is actually, taking this integral is not necessarily something that, that they're expecting that you know how to do. But I suspect many of you, maybe all of you, know how to do that integral. But this last step isn't necessarily, it's not essential that you know how to do that antiderivative. So then let's think about what this whole thing is going to turn into. Remembering that my variable is y. Well, if y is infinity, it might make sense to you this whole thing is just going to turn into 1. And if y is 0, this whole thing is just going to turn into 0. Which means now that the magnitude of b, maybe I'll write this down here, the magnitude of b is going to be equal to mu naught I over 2 pi x. And this whole thing just turns into 1, which is kind of an interesting and non-trivial result. We'll find ways of deriving that using Ampere's law that are a little bit simpler. If I wanted to write, by the way, I guess I could get rid of these and we could just find the b vector, and then we would just have to put it, we just have to indicate that the direction is, maybe we could call that, I don't know, in our world we might, if we called this the y direction, sorry, this is the y direction, that's the x direction, that would be like the negative z direction, so negative k hat maybe, something like that, if we wanted to give the direction. So that's a quick intro into the biot-savart law. You're going to have a chance to practice it in a problem set that involves a few different problems, different cases where the biot-savart law will come in handy. Hopefully that was clear. It is a little bit intimidating looking, but I'm sure you guys are up to it. So next video, I think we'll look at Ampere's law.